Last time we discussed partial orders, and in particular, we defined order isomorphism. So we say that two orders A and B are isomorphic, and in particular, alpha is an isomorphism between the two. Alpha is an isomorphism, or let's call it, say, F. It doesn't matter much. If and only if the following conditions hold. So we need our F to be a bijection between the so-called ground sets of our orders, that is A and B. And also we need our function to respect ordering, and that x is less than y if and only if f of x is less than f of y, but now, of course, in terms of our other order b. So two element, if x is less than y, then its image is less than that of y, and vice versa. So that means that our two orderings are structurally identical, so they can be, say, sketched as a diagram in essentially the same way. Modular relabeling, modular changing labels, that is, names for our elements. We have, say, the same order on some other set of elements. This is the idea behind this isomorphism. We can also see that, every poset, every partially ordered set has been defined the following way. So we say that this is indeed the triplet of some ground set, a strict ordering on it, and a non-strict order. A non-strict order, fire away, that is our strict order plus the identity relation. But this begs the question, is it the case that isomorphism respects this ordering as well? We know that by definition it respects less than. But what about less or equal? We shall see that this is indeed the case. Okay, if x is less or equal than y in A, that means that either it is less than y or these two elements are identical. But in the first case, we have f of x being less than f of y in terms of b. And if x equals y, then of course f of x equals f of y. But what do we need for the other direction? What if f of x equals f of y? Why do we have x being equal to z? What do you think? Which property is essential here? What is essential for this implication? So assume that f of x equals f of y. Why does x equal y? Any ideas? Which part of our isomorphism definition is essential here? What is important? One. What do you mean by one? That's not an answer. I see. The first point of our definition. Aha, exactly. So right you are. And in fact, we can even specialize this even more. So f must be injective. As f is injective, surjectivity is not important for this point. If as f is injective, then f of x being equal to f of y implies x being equal to y. So we see that as a result, f of x is less or equal than f of y in B if and only if um, x is less or equal than y in A. So if if isomorphism, according to our definition, if it respects less than, then it also respects less or equal, and it is not that hard to prove that you can you can define isomorphisms in terms of less or equal, and then still it will respect less than as well. Okay. Which properties of isomorphism are important? We can easily prove the following lemma. Every poset is isomorphic to itself. If A is isomorphic to B, then B is isomorphic to A. And this third one, if A is isomorphic to apparently we have some technical problems. Can you see the whiteboard? And now, did it improve? Okay, thank you. So, if A is isomorphic to B and B is isomorphic to C, then clearly A is isomorphic to C as well. But how can we prove it? In order to prove that, we have to specify some isomorphisms. What is an isomorphism? An isomorphism that guaranteedly exists between A and A. What could you propose between A and A? Identity, exactly. And now assume that F is an isomorphism, hence a bijection between A and B. What do we have with B and A? Do we have an isomorphism from B to A? Which one? Yeah, exactly. We can take the converse relation, which is also a bijection, and it is not hard to check that it is indeed an isomorphism. So let us check. So assume that we have some U and V being elements of B, and we have that U is B less than V. What do we have? We have that by bijectivity of F, there exists a unique such X and there exists a unique such Y, so that U is F of X and V is F of Y. Hence, what does that mean? That means that F of X is B less than F of Y. But as F is an isomorphism, as F is an isomorphism, that means that X is A less than Y. But on the other hand, what is X? X is, of course, F converse applied to F of X. And here we have the same. So this is equivalent to F converse of U being less than F converse of V. I hope it is quite clear. And what do we have here? Assume that we have an isomorphism F from A to B and G from B to C. Which isomorphism can one have from A to C? The composition, exactly. We know that composition of two bijections is itself a bijection. And it is not that hard to prove that it also preserves our order. Okay, so far so good. Last time we discussed some examples of isomorphic and non-isomorphic orders. And now let us see which properties can also be preserved by isomorphisms. It is quite important to understand that every property, of course, it is somewhat vague, it is somewhat non-rigorous. You need mathematical logic in order to make this statement, this claim rigorous, but nevertheless, it appears that every property you define in terms of orders, of orders alone, every such property are preserved by isomorphisms. For example, minimum is defined in terms of our orders, that is, which element is minimal in a set. Every element which has nothing less than it in that set, so it is defined relative to our set, of course, in terms of our order. So that means that an isomorphism would map such an element to another minimum. A minimum in which set? In the image of our set in question. And for example, if we have a property of our whole order, for example, we know that it is linear, then any order which is isomorphic to ours is also linear. So everything defined in terms of order is preserved by isomorphism. So let us state some examples of this rule, of this fact. So assume that we have two orders A and B, and some isomorphism F between the two. So we have the following. For example, A is, say, linear if and only if B is linear. For every x, for every subset of A, we see that, say, minima of x are mapped to minima of what? It is not alpha, by the way, it is f. To minima of the image of this set. Some other examples. If we have, say, supremum, a supremum of x with respect to the order of A, then its image, it will be mapped to the supremum of still not alpha, but f. Supremum of the image with respect to our order. And of course, we can say the same for chains, anti-chains. Say the image of any chain is a chain the image of any anti-chain is an anti-chain. Infimum, if it exists, is mapped to infimum of the image set, and so on and so forth. So we can say and so on. And so on. Of course, one has to prove every such point formally, given we have no general statement for this theorem that everything defined in terms of an order is preserved. How can we prove, say, the second claim? Let us prove the second claim. So assume that something is a minimum. So let say y belong to the set of minima of x. What does it mean? It means that y belongs to x and no z from the same set is less than, nothing is less than our y. What does that mean? That means that for every z in x, the image of this z is not less than f of y. So there is no f of z which is less than f of y in B. And on the other hand, of course, from here we know that f of y belongs to the image of x. So it belongs to this image, but still there is no element of this form which is less than f of y in this set. But we can see that every element, we can see that anything, every u that belongs to the image of x, for every such u, there exists a unique z in x, such that u is f of z. So if it holds for every z from x, it appears that it holds for every u from the image. It holds for every u from the image because every u from the image is expressible in this form. So no u here is less than f of y, but still f of y belongs to this set, and this is equivalent to the fact that f of y is a minimal element in f of x. Of course, formally we had one-sided arrows here, implications from the left to the right. But it is not hard to prove vice versa, that if f of y is a minimum in this set, then y itself is a minimal element here. It is also quite easy to prove, and moreover, you can apply this fact that if A is isomorphic to B with F, then B is isomorphic to A with F converse. So if you know that every minima from X is mapped to a minima of F of X, then you can take this set and you can see that every minimum of this set is mapped by F converse to the minimum of F converse of F of X, that is just X. But I will skip the remaining details as they are not that important. But we shall know quite well that everything, every detail, every feature of our order, which is defined in terms of this order alone. So It doesn't depend on our exact elements. Say there is no mention that x is, say, even or is a number, something like that. Every feature which is defined in terms of just our order is preserved by isomorphisms. Okay, do you have any questions so far? Okay, now let us move on and consider some other concept you may be already familiar with. This is that of equivalence. So equivalences. Equivalences are widespread and very common in our everyday life. So you can say that somebody is of your age. Somebody is of your age. What does it mean? Most likely this doesn't mean that that person was born on the very same date, the same hour, the same minute, second, and so on. So that means that, say, the years of your birth are identical. For example, so that means that that person is roughly of your age. But now let us look at this being of the same age as a binary relation. Let us look upon that as a binary relation. X and Y are of the same age. Say X and Y are of the same age. They are of the same age. What does it mean? Let us somehow denote it like age of X and Y. It is a binary predicate. Which properties do we surely have? Is it the case that everyone is of the same age as himself? Surely. If X is of the same age as Y, then also Y is of the same age as X. If X and Y are of the same age, and Y and Z are of the same age, then most surely X and Z are also of the same age. But these properties, when binary relations are concerned, are respectively called reflexivity. Our binary relation contains every pair of identical elements. Reflexivity, this one. The second one is which property of a binary relation? Symmetry. Yeah, exactly. This is symmetry. And the last one? The last one is, of course, transitivity. So this relation to be of the same age is reflexive, symmetric, and transitive. You can consider many other relations of the same kind. Say, to be of the same nationality, of the same citizenship, whatever, your compatriots, say, citizens of your country. So this is also reflexive. You are always compatriotic to yourself. If X and Y are compatriots, that is citizens of the same country. They are Y and X are also compatriots, and also it is transitive. Or say you can think of persons of roughly the same height as you. This is also must be reflexive, symmetric, and transitive. In mathematics, we also have a plenty of such relations which are reflexive, symmetric, and transitive. Above all, we know that identity itself satisfies all these properties. But now we are interested in more general idea, more lax conditions. So identity is, of course, is reflexive. It is reflexive for the set A. It is symmetric, and it is transitive. But it is not only such a relation. For example, let us take A squared, that is A times A. So assume that we are taking all the pairs of elements from A. Is it reflexive? Is it the case that every pair of identical elements belongs to this set, the set of all possible pairs? Clearly it is. If we schematically depict this A times A here is our square, then the diagonal of this square will be just the set of all pairs of identical elements. So it is clearly reflexive for A. It contains every pair of elements from A. Much more so, it contains every pair of identical elements. Is it symmetric? Clearly it is. If x and y, if xy is a pair of elements from A, of course yx is also such a pair. Is it transitive? It is clearly transitive, as you know. Transitivity means that under some condition, given xy belongs to our relation and yz belongs to our relation, then under some condition xz belongs to our relation. But if we look at A squared, we know that for every x, y, and z from A, this pair belongs to A squared. So this is, of course, always true. It is reflexive, symmetric, and transitive. So identity is reflexive, and even the greatest binary relation on A squared itself, is also an equivalence. It is reflexive, symmetric, and transitive. By the way, let us give a formal definition. We say that a relation A on a relation E on A is an equivalence, or sometimes they say equivalence relation is an equivalence on A if and only if these three properties hold. That is, E is reflexive for A, E is symmetric, and E is transitive. E is transitive. And so for now we know that identity and A squared are always equivalence relations on A. By the way, let us denote ec of A the set of all binary relations which are equivalences on A. So we are taking all the subsets of A squared, that is all the binary relations, and pick up just those of them which are equivalences. which is an equivalence on A. So this is a set of all our equivalences, much like there was a set of all others. And now we know that identity and A squared are always equivalences on A, and moreover, we can see that these are, in a sense, the least possible and the greatest possible equivalences. Look, if E is an equivalence relation, then clearly E is reflexive by definition for A. Hence, the identity relation is a subset of E. So what do we have? We have that for every equivalence relation on A, for every equivalence relation E is greater or equal in terms of set inclusion, is greater or equal than ID, than the identity relation, and as every relation on A, it is of course less or equal than A squared. So every equivalence is in between E and A squared, in between identity and A squared, where the identity relation and A squared are also equivalences, the least possible and the greatest possible equivalences. Let us consider more examples from mathematics, except this identity. What do we have? I have said that equivalence is some generalization of identity, still reflexive, symmetric, and transitive, but not necessarily identity. What can we name for, say, integers? Which very prominent equivalence do you know? On integers, you should know, as you have your discrete mathematics course under Professor Yelishev. You should know that quite well. He has surely taught you about that relation. Think of integers. Which binary relation is reflexive, symmetric, and transitive? For integers, but still not necessarily an identity. Gentlemen, any ideas? No idea. Addition, no. Addition is not a binary relation on Z. Look, it is ternary because you have first summand, second summand, and the result. So addition cannot be treated as a binary relation on integers. Not that. Something else? Something else, gentlemen. Have you ever heard of congruence modulo M? Congruence. Okay, this symbol. What does it mean that A is congruent to B modulo M? Have you learned that? Gentlemen, the screen disappeared. And now, can you see it now? But anyway, Congruence modulo M. Have you heard of that? We need an example of an equivalence relation on the set of all integers, something natural, something very easily coming to our minds. An example of an equivalence relation on Z, on the set of all integers. That is my question. Equivalence set. Of course, it is an equivalence when restricted to some set of sets. But still, we are speaking about integer numbers. Look at that. Can you see the whiteboard? By the way, you can switch your microphone on. And it would be more comfortable for me. F of n equals twice n. It is a function that returns even numbers, but it is not an equivalence relation. No. Look at that symbol. Look at that symbol I am highlighting in red. Do you know what does it mean? Do you know what it means? Can you see the whiteboard? You have forgotten the name. Yeah. The name is as follows. A is congruent to B modulo M. A is congruent to B modulo M. But what does it mean by definition? Do you know the definition for this symbol? The definition. But what is that? Please recall the definition. When A and B are congruent modulo M. What does it mean that they are congruent? They leave the same remainder. Yes, this is one possible definition. But most likely, they take some other property as the definition. They take the following. The difference of A and B is divisible by M. And by easy theorem, this is the same as the remainder. This is equivalent to the following. The remainder of A after dividing by M equals the remainder of B after division by M. Do you know that? Or don't you? Yeah, or A minus B. No. Not A minus B divides M, but vice versa. M divides the difference. M divides the difference. So that means that the distance between these numbers is in full units of M. Is in whole units of M. So what do we have? Say, let us take, say, I don't know, minus 7 and minus 7 and say 14. Minus 7 and 14. I say that they are congruent modulo 3. What does it mean? That means that their difference, that is minus 7 minus 14, which is minus 21, is divisible by 3. And it clearly is. So if we depict them on our integer line, so what do we have? We have minus 7 here, we have 0, and here we have 14. And we know that the distance between these two numbers is in full units of 3. Minus 7, minus 6, minus 5, minus 4. 3 points. From minus 4 to minus 1, 3 points. From minus 3 to 2, 3 points. From 2 to 5, 3 points. From 5 to 8, 3 points. From 8 to 11, 3 points. From 11 to 14, 3 points. So their distance is in full units of 3. Is this idea clear? Minus 2 is congruent to, minus 4 is congruent to 10. But which modulo? Modulo 7. Yes, they are, of course. Minus 4 is congruent to 10 modulo 7. That's it. But anyway, we have many examples. But what is important here is that this is an equivalence relation. So why is it reflexive? We know that x is congruent to x any modulo m. Why is it the case? Because x minus x is just 0, and 0 is divisible by any number. It is symmetric. We know that if x is congruent to y modulo m and y is congruent to symmetry, then y is congruent to x, the same modulo m. That means that if m divides x minus if m divides x minus y, then of course m also divides y minus x. It is also quite obvious. And also it is transitive. It is also transitive. It is not hard to prove that it is transitive. By the way, usually they skip this word mod and just this m in parentheses remains. So if x is congruent to y and y is congruent to z, then x is also congruent to z. I will skip the proof, but it is quite easy to prove it from either definition. From this one, it is obvious because the remainders are the same for x and y and for y and z. The remainders are equal, hence the remainders for x and z are also equal. So we see that this congruence modulo m, which we can also denote some other way, like that. This is the same. Another way to say the same thing. Another way to say the same thing. We know that this congruence for any m, usually they are considering integers greater than 1. For any m, this congruence is an equivalence relation. It is an equivalence relation. And this is a natural example of equivalence relation. But look, we know from a theorem of your number theory of a discrete math course that A is congruent to B modulo M. We know that A is congruent to B modulo M if and only if the remainders modulo M are equal. But look, with M fixed, we can consider that as a function. M is fixed, so we say we can consider that as a function, some function. And now we are going to say that the values of this function at A and B are equal. So A is congruent to B if and only if some function's value, that is the remainders are equal. A is equivalent to B if and only if some function values are equal. And it appears that this is the general situation. If we consider some other equivalences from our everyday life, say two persons are of the same age. When they are of the same age, when some function value equals for them. So we say that X and Y are of the same age if and only if their ages equal. And this situation is general. I won't prove it now, while it is not that hard to prove, but it is somewhat abstract. But I'll just give you the definition. For every function, we have a special binary relation, some special equivalence concerning this function. This is known as the kernel of that function. Let f be a function from A to B. Let f be a function from A to B, whatever function, whatever sets A and B. Then we shall define the following set of pairs, the following binary relation known as the kernel. The kernel of f, like your operating system, say kernel. xy belongs to A squared if and only belongs to the kernel if and only if f of x equals f of y. So we may see that, this binary relation, congruence modulo M, is just the kernel of which function? Of this function, of the function that maps every element to its remainder modulo M. H is the kernel of the function h, and so on. It appears that every equivalence relation is a kernel. But let us prove that. Let us prove the following statement: that for every such function, its kernel is a binary relation, is an equivalence relation. Let us prove this statement. It is very easy to do so. Still, we need reflexivity. We need reflexivity. Why is it reflexive? Okay. What does it mean that xx belongs to the kernel? That means that f of x equals f of x, which is clearly true. Which is clearly true. So this is also true. Symmetry. Assume that xy belongs to the kernel. Then by definition, f of x equals f of y. But we know that equality is symmetric. Hence, f of y equals f of x. So by the same definition of our kernel, yx belongs to the kernel of f. And the last one, it is transitive if x and y and yz, these two pairs, belong to the kernel of f. That means that f of x equals f of y, f of y equals f of z. Hence, of course, f of x equals f of z, and xz belongs to the kernel of f. So this kernel is always reflexive, symmetric, and transitive. Hence, it is an equivalence relation. This kernel can be considered as some measure of non-injectivity of our function. Let us prove the following easy theorem. We say that f is injective if and only if its kernel is... Any ideas? By the way, gentlemen, have you understood what kernel is? Have you understood that? Kernel is just the set of pairs our function mapped to the same value. So the set of pairs which are glued together, which our function cannot discern, which our function treats identically. Is this idea clear? This is called the kernel of our function. An example, here it is. If I have a function age that maps a person to his or her age, then the kernel of this function will consist of all pairs of persons of the same age, all pairs of persons of identical ages. If I take function remainder, its kernel will be remainder modulo m. Its kernel will be this equivalence. But maybe you need simple examples. Okay, let me give it. Assume that we have some finite function from 1 to 3 to say 4, 5, 7, or 6. Assume that this function maps 1 and 2 to 4 and 3 to 5. What is the kernel of this function? This kernel consists of all pairs of elements for which function values coincide. So for which pairs the values are identical. So 1 and 1 are mapped to 4. So this pair belongs to the kernel. 2 and 2 are mapped to 4. So this pair, 2 and 2, belongs to the kernel. 3 and 3 also belongs to the kernel. But what else? Which other elements are identified? Yeah, exactly, 1 and 2. 1 and 2. But what about 2 and 1? It must be symmetric. And of course also 2 and 1. So kernel is the set of pairs which are treated identically by our function, which our function cannot discern. So when f is injective in terms of kernels, Any ideas? Is injective. Yeah, when f is injective, when its kernel is injective. No, its kernel is not injective. Or is it? It is. It is. Yeah. In fact, that's nice. It is injective. Yeah. But this is not enough. Not enough. Say, or isn't it? It is. Yeah. It appears that you are right, but your answer is still quite unnatural. But nevertheless, it seems correct. F is injective if and only if its kernel equals the identity relation. This is obvious. So our function is injective if and only if it identifies identical elements. So there are no non-trivial pairs. So say in this example, our function is clearly not injective. That's why we have pairs of not non-equal elements here. Is this idea clear? Your definition for kernel is from linear algebra is something else. This is something else. Okay. Let us compare our kernel with that of linear algebra. But please notice that in linear algebra, you require that identity element of B. But here, for arbitrary sets, we have no identity element. What is an identity element? What is that? So in linear algebra, A and B are linear spaces, or at least groups. And then kernel in algebraical meaning is what? It is a set of all x's from A indeed, such that f of x equals 0 of B. And B is, say, linear or in general homomorphic. Have you had homomorphisms? So this is the pre-image of 0. But what do we have in fact? We see that x belongs to this kernel. Notice this capital letter. X belongs to this kernel if and only if f of x, yeah, equals 0. But as f is linear or homomorphic, that means that f of 0 always equals 0. So that means that f of x equals f of 0 for our neutral element. That is, the pair x0 belongs to the kernel in our sense. So this is the relation between our kernel and that of linear algebra or group theory and so on. So these are linear spaces or generally groups. Is this idea clear? Okay. So what is also important about this equivalences? Assume that E is an equivalence relation. Say to be of the same age. To be of the same age. How could you define, say, your generation? What is your generation? It is a set of persons of what? Of the same age as you. Yeah? So everybody that is of the same age as you, if you pick all such persons together, you will obtain a set of persons, and this set deserves a name of your generation. Deserves the name of your generation. Okay. Let us see what we have in mathematical setting. Let E be an equivalence relation on A. Let X be whatever element in A. So we shall define this set, this X in square brackets. This set will be called the equivalence class. The equivalence class of X with respect to E. What is that? It is just the set of all elements. The set of all elements in A which are equivalent to our X. Just that. For example, if we consider our example with congruence modulo M. Congruence, say, modulo 3 is an equivalence relation on Z. Which elements are equivalent to, say, -5? What is an equivalence class of -5? Modulo 3. Which are these elements? All such numbers which are congruent modulo 3 to -5. But modulo 3, -5 is congruent to what modulo 3? One. Exactly. It is 1 modulo 3. So what do we have? This set consists of what? 1, 4, 7, 10, 13, 16, and so on. And on the other hand, we have negatives. We have negatives. -2, -5 itself, -8, -11, and so on. So all these numbers comprise this equivalence class. Is this idea clear? So the equivalence class of an element is just the set of all elements equivalent to it. For equivalence classes, we have the following important theorem. Lemma says 3. Let E be an equivalence on A, and let X and Y be some elements in A. So what do we have? First of all, every element belongs to its equivalence class. And second, two equivalence classes are equal if and only if X and Y are equivalent, if and only if they are not disjoint. If two equivalence classes have a common element, if they are not disjoint, then X is equivalent to Y and vice versa. And also this is logically equivalent to saying that our equivalence classes are equal. So in other terms, distinct equivalent classes are disjoint. If they are distinct, they may have no common element. Let us prove this important theorem. For the first one, we have that E is reflexive, hence X E X. So we see that X clearly belongs to its equivalence class. I will generally skip this subscript E. I will skip it. So because we have no other binary relation in our context. So this is quite clear. For the second one, okay. First of all, A, B, and C. Let us prove three implications. For the first one, assume that these two sets are in fact not disjoint. Then, of course, there exists some Z that belongs to both of them. That is, we have X E Z and Y E Z. Our Z is equivalent to each of these elements. Now let us apply symmetry. As E is symmetric, we have still X E Z and Z E Y. As it is transitive, we have X E Y. That's it. We have proved that if two equivalence classes are not disjoint, then these elements, by the way, these are known as class representative. So this is known as a representative. A representative of this class of X. In fact, you can take any element of this class as its representative. This theorem says exactly that. Two classes are equal if and only if their representatives are equivalent. So from this one to this one, from this one to this one. If X is equivalent to Y, then the classes are equal. B. Assume that X and Y are equivalent. We want to prove that two sets are equal. So we want to prove that anything equivalent to X is also equivalent to Y. And of course, vice versa. Everything equivalent to Y is also equivalent to X. Let us look at this one because this is similar. What do we have? Assume that some Z belongs to the class of X, that is X, E, Z. So we have X, E, Z, but also by our assumption, we have X, E, Y. So we can do what? Let us apply symmetry. Applying symmetry, we have Y, E, X, and X, E, Z. Applying transitivity, we have Y, E, Z, and symmetry, and that's enough. That's enough by definition. That means that Z belongs to the class of belongs to the class of Y. So everything in the class of X also belongs to the class of Y. That's it. And see, if these two classes are equal, then they are not disjoint. This is obvious. If they are equal, they have a common element. Which one? X, say. We require that there is some common element. It's very easy. So we have that X belongs to X by our first claim, which equals the class of Y. So we see that X belongs to both these classes. That's it. So, gentlemen, I cannot let anybody to our class because the entry is free. So there is no need in any action on my part. Just join and that's it. So is this theorem clear? We have just proved that first of all, any element belongs to its equivalence class. Two classes are equal if and only if they are not disjoint. That is, if they are not equal, they are disjoint. As a corollary, now we know that if X differs, if two classes are different, then they are distinct. They have no common element. What does it mean? What does it mean in practice? If we have A, we can take whatever element X, and then this element is covered. That is, it belongs to its equivalence class. But it cannot belong to any other equivalence class, because if two equivalence classes are distinct, they have no common element. So somewhere here there may be an element Y which is not equal, not equivalent to X, and it will belong to some other class, and so on. So these classes comprise a partition of our set. They comprise a partition of our set. What is a partition? Let us discuss this point in some detail. First of all, here we have defined the class for an element. But can we consider all possible classes for all possible elements? If we can, what the result will be? We can define the so-called quotient set. Let E be an equivalence on A, and so we can define the following set, which is known as the quotient set. It is known as the quotient or factor, of A by E. What is that? Simply put, it is just the set of all equivalence classes. Every equivalence class, by the way, is a subset of A. the set of all equivalence classes. For example, if we take integers and consider equivalence classes, which are that? How many equivalence classes would we have? We will have equivalence classes of 0, of 1, and of 2. Why no more? Because every x, for every integer, we have that this integer is equivalent to either 0, or it is congruent to 1, or it is congruent to 2, because there are just three distinct remainders, modulus 3, 0, 1, and 2. So we have just three classes. Here they are. The first class consists of all numbers that are multiples of 3. So it is 0, plus or minus 3, plus or minus 6, plus or minus 9, plus or minus 12, and so on. The second class consists of 1, 4, 7, 10, and on the other hand, minus 2, minus 5, minus 8, and so on. And the last class consists of numbers that leave 2 as the remainder. So here we have, of course, 2, 5, 8, 11, 14, and on the other hand, minus 1, minus 4, minus 7, and so on. So we have three classes. Look, after this operation, after taking the quotient, our infinite sets of integers has been mapped to a finite set. So it have somehow diminished in its size. So it was infinite, but after identifying elements with the same remainders modulus 3, it have become finite. So now we have just three classes. Numbers divisible by 0, including divisible by 3, including 0, including 3, or whatever. Numbers that leave 1 as the remainder, and numbers that leave 2 as the remainder. For example, here we have, say, 4, and here we have 5. We have somehow split our set into disjoint parts so that no part is empty. Distinct parts are disjoint, that is, have no common elements, and every element belongs to at least one part. Any such set of subsets, we may split our set A in, is known as a partitioning or partition of our set. Anything like that is known as a partition of our set A. And we see that factor is always, a quotient set is always a partition. We can define partition abstractly. Let us do that. Assume that sigma is some set of subsets. For example, like our quotient set, it is a set of subsets. Assume that sigma is a set of subsets. We say that sigma is a partition. It is a partition of A if and only if the following statements hold. First of all, no element in sigma is empty. No element in sigma is empty, or in other terms, as the empty set is unique, that means just the empty set doesn't belong to sigma. Nothing is empty. Every element in A belongs to at least one element of our partition, at least one piece of our partition. And in fact, every element in A belongs to at most one piece in our partition. That is, if for every two pieces, if they are not equal, if they differ from each other, they have no common element. So nothing can be a common element of two distinct pieces. By the way, these two are equivalent to the following. For every x, there exists a unique piece of our partition that contains x. So this is like splitting our set into some parts. For example, we can schematically depict it this way. Sigma 1, sigma 2, sigma 3. Notice that every element belongs to exactly one piece. And sigma is just the set of these pieces. Not, generally speaking, the elements of our set, but its subsets. And we see, as a corollary, we see that the quotient set, the set of equivalence classes, is always a partition. It is always a partition. For every equivalence, is a partition of A. In fact, it is not hard to prove that any partition is a quotient set for some equivalence. But I will omit this result. We can read about it in my lecture.